And this is the final video in this series on using fundamental relations, Maxwell relations, and measurable quantities. So the last thing we want to do is talk a little bit more about Gibbs energy. Gibbs energy turns out to be our favorite of the energy functions in chemical engineering. One of the primary reasons is it's naturally a function of the two easiest variables to measure, P and T. So that says that dG equals VdP minus SdT, which is all well and good, but sometimes it's really helpful to have a dimensionless form. And so in this case, if I divide by RT, I can get this into a dimensionless form. So just dG over RT, I can apply the differential definition here. I get 1 over RT dG minus G over R derivative of 1 over T, which is dt over T squared. Now if I use this plus the fundamental relation here, okay, I end up with 1 over RT times VdP minus SdT minus G over RT squared dt, which gets us this. Okay, so I have a dt here, I have a dt here. Let's combine them. I end up with V over RT dP minus G plus ST over RT squared dt. Now this may at the moment look like, oh my goodness, what a mess. But G plus ST, if you play with the variables a little bit, turns out that that's exactly the same thing as H. So V over RT dP minus H over RT squared dt is the change in G over RT. Now, H is usually well tabulated, so we frequently have this as data. So this is actually a useful relationship, and we're going to find, as we continue in the course, some other ways that these quantities are useful. Now, there are other dimensionless forms. So G over RT is one that we frequently end up with, but occasionally you'll also see things for S. Its dimensionless form is divided by R. So S over R is H over RT minus G over RT. And U, all the energies are divided by RT, so U over RT is H over RT minus PV over RT. You might recognize that last little grouping there as something very familiar. Now, I said that I wanted to show you that this really is practical, what we're doing. So here I've got a problem. We want to combine what we know about the first law, the second law, use limited data that we might find available to actually solve problems. So here I've got 1 mole of propane. I'm going to expand it from 0.001 cubic meters to 0.04 cubic meters. It's going to be in a heat bath that's going to hold it at a constant 100 degrees C, so temperature will be constant. Now this expansion is not reversible, it's just a real process. The heat extracted from the bath is going to be 600 joules, and we want to use the van der Waals equation of state to determine how much work is going to happen in this expansion. So if you look at the first law, I can end up with the work and plus Q is equal to delta U. It's a closed system. Now Q is 600 joules, so I end up with an expression for work as shown here. I now need to figure out what delta U is. Well, this is going to be a process where I'm calculating delta U, and the variables that have been described to me are volume and temperature. So I want to look at how U changes with temperature and volume, the two variables stated in the problem. So this is what I end up with, and from the previous work we know this. Okay. dP dt at constant volume. They said I can use the van der Waals equation of state. Well, the van der Waals equation of state is fortunately written as P equals an expression in terms of volume. So I will be able to take this derivative with respect to temperature holding volume constant. So that's actually going to turn out to be a fairly easy little expression, right? Okay, so we're going to end up with this. dP dt at constant volume okay, is going to be r over v minus b. Multiply that by t, and I get RT over V minus B, which is this expression right here. Okay? Take that and subtract P. Okay, well, again, P is this expression right here. So RT over V minus B minus RT over V minus B minus negative A over V squared. So I end up with plus A over V squared. If I go back and look at this, CV dt, again, I'm holding t constant, so this is going to integrate to 0. I now have a over v squared here, dv. If I want to know the change in u, I can integrate for the change in v. So I end up with this. Doing the integration, we end up with that expression. And now I simply need to find values. So for a van der Waals fluid, I have a definition for A in terms of critical properties. Critical properties for propane are shown. Again, we're talking about a case where you have limited data available. And so we end up with A as 0.96 joules times cubic meters per mole squared. Substituting in for delta U, I end up with 936 joules per mole. Subtract off that 600 joules per mole of heat, and the work is going to be 336 joules per mole. So the key to working one of these problems is, first of all, read the problem statement and see which two variables they're talking about changing or holding constant. Okay? And then apply your first or second law as needed. When you get to an expression where it's like, oh, I have to get data, if you don't have data, use these definitions of fundamental relations, Maxwells, to get these into things that we can use limited data to come up with an actual physical number. All right, this concludes Module 9. In Module 10, we're going to be looking at what happens when I have not just one single phase, but two phases.